hopefully you can.
Okay, go ahead.
Yeah, can you see my slides all okay?
Yeah, it looks good.
Excellent, wonderful. Great, so thanks Ingrid. As Ingrid said, I'm Catriona McDonald. I'm a third year PhD student at the University of Warwick in the UK. And today I'm going to talk to you a little bit about some of the work my supervisor and myself carried out over the last year and published last year about modelling the origins of white dwarf debris systems. So first of all, just as a little bit of a background to white dwarf debris systems. So current estimates are that between 25 and 50% of all white dwarfs have evidence for metals in their photospheres, which can only be present if they had recently been accreted due to the fact that white dwarf atmospheres readily sink metals into their cores. So we shouldn't be able to see them unless they were recently put there. Further, 2 to 3% of these white dwarfs host dusty debris disks, and 0.03 to 0.01% host gaseous debris disks. So there is definitely material around and in white dwarfs that shouldn't necessarily be there. We can make some sort of estimates about where this material has come from based on the composition of the material itself. So on the right here, I've stolen a plot from Doyle et al. 2020, which shows the normalized concentration of the 6 major rock-forming elements in the solar system inside 16 polluted white dwarfs, which are towards the right-hand side of the plot, so from here onwards. And on the left-hand side is some sort of typical solar system bodies, so chondrites, so asteroids, bulk Earth, and solar concentrations. And you can see that pretty consistently these materials inside these white dwarfs align quite nicely with rocky material, which we have in the solar system. So the question then kind of becomes, how do we get this material into the white dwarfs? And to sort of understand this mystery a little bit better, I want to give you a quick run through of how planetary systems evolve along with their stars. So in the top left-hand corner here, I have a sort of sketch of a main sequence planetary system. So we have the star in the middle, some inner planets, a planetesimal belt, this sort of white dotted bit here, and some planets even further out than that. Now, when the star moves on to its giant branch phases of its lifetime, it increases in size massively and also increases in luminosity, which has a really large effect on its planetary system. The size increase can actually engulf inner planets in its common envelope, and the mass loss pushes the rest of the planets out onto orbits, which are 2 to 3 times wider than they were during the main sequence. The luminosity also has a large effect on planetesimals that are close to the star, so sort of within 7 AU, where they can effectively be broken down into their smallest parts due to the increased amount of stellar radiation. So this all means that when we move on to the white dwarf phase at the bottom here, and we are left with a star that is just sort of an Earth radius in size, the inner regions of this planetary system should be completely devoid of large planetary material. And the rest of the material in forms of planetesimals and planets will be on quite large orbits away from the star. So how do we get this material into the white dwarf, where we observe it in the form of debris disks and pollution? So the canonical theory that we have at the minute is that we have an asteroid, which here is denoted in green, on a very large initial orbit, so this dashed line which sort of goes off the edges of the slides here, which sort of encounters a planet and undergoes a perturbation, which throws it onto an extremely eccentric orbit, which is shown by this solid green line, which allows it to cross into the Roche radius of the white dwarf. So when it crosses this Roche radius, the tidal forces from the star are stronger than the internal forces of the body and are able to tear the body apart, which is how we think we form these debris disks. So I just want to say, Brouwers, Bonza and Malamud released a paper earlier this year called, which gives a very detailed roadmap to this pollution. So please have a look at that if there's any sort of other ideas about this canonical theory. So this canonical theory quite nicely matches up with the first transiting debris system we observed back in 2015. So I've highlighted the light curve for this observation in red in this top right-hand corner here. And the inferred orbit for these planetesimals around this WD1145 plus 017 is that its orbital period is about 4.5 hours, which means that its semi-major axis, or how far away it is from the white dwarf, is about 1 solar radii, which is coincidentally about the Roche radius for this system. So this seems to match up quite nicely with our canonical theory of tidal disruption, as I sort of mentioned in the the slide before. And this wonderful plot of light curves from Guidry et al. 2021 also sort of shows some candidate systems underneath. In fact, this purple one here has since been confirmed, but there's now like 4 systems on this similar orbital period, which all seem to confirm the canonical idea. But if we move to the left-hand side of this plot, and the second transiting debris system, which I've highlighted in red, ZTF J0139, we have a sort of completely different set of orbital circumstances. So this object, the orbital period is about 110 days, which means that its semi-major axis is about 100 times larger than that around WD1145. And so it needs an extremely high eccentricity, so larger than 0.98, in order for it to cross into the Roche radius of the star. So we know that these objects, if they are undergoing this canonical theory of tidal disruption, have to be on very eccentric orbits, and sort of modeling how the objects react to these eccentric orbits is what this work aims to do. Oh, and also there has been 2 more candidates also reported in this Guidry paper on similar long orbital periods. So myself and my supervisor wanted to look at the effect that, using the wonderful knowledge we have from solar system asteroids, and if there are any sort of implications from that knowledge that we could apply to our understanding of white dwarf planetary systems. So the one thing that solar system asteroids make abundantly clear is that asteroids are not spherical. And although spheres make it really easy to model systems, it might not be the best way to do it when we're talking about bodies which can have all sorts of shapes, such as Bennu, Cleopatra, and Oumuamua, as shown here. So we modeled the evolution of triaxial ellipsoidal asteroids. So this sort of sketch on the top right-hand corner here shows just a generic triaxial ellipsoid and the 3 separate semi-axes, A, B, and C, which we can use to define the size of the ellipse. And in the middle, this B and these stylized B and C values are aspect ratios, which describe effectively the shape of the asteroid due to the ratio between the different semi-axes. So in this work that I'm sort of discussing here today, there's a few separate shape models we consider, so oblate, prolate, and generic, which are all based on different combinations of these aspect ratios. So your oblate asteroids are sort of a typical ball that has been squashed downwards. Prolate are ones that have been squashed from the side, and a generic asteroid is any sort of ellipsoid, is any sort of combination of these 2 values. But you can also describe some of the more extreme asteroid shapes, like Oumuamua, with prolate asteroids as well. So we want to know, how does this shape affect the process of an asteroid approaching a white dwarf? So we designed this sort of analytical model, which is initially an expansion of the work presented in Brown, Virus, and Gansica 2017, which considers a planetesimal approaching the white dwarf on a really eccentric orbit, whose pericenter is effectively inside the white dwarf photosphere. So I should note here that we don't actually consider the orbital movements of these asteroids at all. We just consider that they are moving or how they were perturbed. We just consider that they are essentially moving on a straight line towards the white dwarf, and how do they evolve from there. We consider 3 separate material compositions of these asteroids. So snowy, which is basically a cometary material, so very weak in very low densities and very low internal strengths. Rocky, which is your more typical asteroid, so sort of chondritic-like, a mixture of more solid dusts and ices with a higher density, and also iron bodies, which are solid and quite rich in iron. And this is an important one to consider based on the inference of a planetary core fragment orbiting inside the gaseous debris disk around SDSS 1228 from Manser et al. 2019. So we know that there are these extremely dense objects in white dwarf systems. We want to sort of consider the full range of possible materials. So for our analytical model, we sort of outlined 3 separate outcomes that we wanted to know when they would happen based on different properties for the bodies. So the first is total sublimation. So this will occur when all of the mass from the object is lost due to the sublimation of its material due to the stellar radiation. Secondly, fragmentation. So when the tidal forces from the star are able to overcome the body's own gravity and it is torn into smaller parts. And thirdly, direct impact. So at this point, if the body doesn't sublimate or fragment, is it able to impact directly onto the surface of the white dwarf based on our orbital assumption that the pericenter is inside the white dwarf's photosphere? So the analytical model we sort of designed can be broken down broadly into this one flowchart here, which sort of answers all of the questions. So how does the size of the asteroid, so how does the size of each ellipsoidal semi-axis change due to the sublimation from the star? So how does it change as mass is lost, basically? So we can then ask, is all of the mass lost due to the sublimation at some point during its orbit? If yes, we define that it sublimates completely. If it doesn't, we then ask, does the instantaneous size and location of the asteroid ever coincide with the specific condition for the body to fragment? If yes, it fragments, and if no, it impacts directly onto the white dwarf photosphere. We can also show this in a sort of simple graphical way here. So in this plot here, the y-axis is slightly deceptively named, but when it says asteroid semi-major axis, it actually means the largest semi-axis of the ellipsoidal shape model. So the y-axis is effectively a proxy for size, whereas the x-axis is the distance from the asteroid to the white dwarf. And the white dwarf is sort of signified by this grey block on the left-hand side here. So your body will enter into the plot from the right-hand side and move to the left towards it. Now, the grey dashed lines on this plot show how the semi-axis changes, so how the size of the body changes due to sublimation. And you can see that largely for the sizes shown here, they really don't change too much until you get to this very small size, where you begin to see a sort of curling down where mass is starting to be lost here. Whereas the diagonal colored lines show the condition for fragmentation. So effectively where the individual Roche radius for this object would be. And so as the asteroid moves from right to left, if it crosses this particular condition at any point, that's when the object will fragment. And if neither of these conditions are ever met, then we get the impact onto the surface of the white dwarf. So again, because we were primarily looking at how does the shape affect these models, the first thing I wanted to show here is how the shape really does quite affect the sublimation for these bodies. So in this plot here, or this diagram here, I'm showing the percentage of bodies of different materials and shapes which sublimate completely as they approach a very hot white dwarf, so a 30,000 Kelvin white dwarf. And you can, if we concentrate first on these colored, these are sort of pink and purple boxes, you can see that for, let's just take the rock as an example, that 62.8% of all prolate, oblate, and generic asteroids all sublimate. But when we consider the more extreme versions of these shape models, so these asteroids which are very long and thin or sort of pancakey, you get quite a large difference in the level of sublimation. So for extremely prolate objects, you actually get about 12% more bodies sublimating compared to a sort of more typical, less extreme asteroid shape. And the same for the two other extreme shape models. You get an increased amount of sublimation based on how extreme the shape model of these asteroids are. But if we move instead to the effect of fragmentation, so how does a triaxular shape model affect the tidal disruption process, we get a slightly different result. So I've just sort of put the sketch back in this top right hand corner here again, so we can remind ourselves of the semi-axis labels. And this plot is essentially the same as the one I showed you previously. So size proxy on the y-axis, distance on the x, and how does the fragmentation condition change for the different semi-axes. So in this case, we are considering the three directions separately, and we're saying when will that particular direction fail? And this particular graph is for the extremely oblate object, but for all of the different shape models, the a-axis, so the longest semi-axis of the asteroid, will always fragment first. And this necessarily isn't that surprising, because the weakest part of any elongated body will always be at the end of its longest axis. So it makes it works out that the largest axis will tidally fragment first. But this does mean that when looking at sort of fragmentation from a analytical way, that you don't necessarily need to consider an ellipsoidal model, because you could just consider a sphere with radius the same length as the semi-major axis here. So moving on from the specific results from the shape of these bodies, we sort of stepped back to think about how a simulated asteroid belt, so an analog main belt from the solar system, how that would react, or how the bulk of the material in such a belt would react if it were to individually be thrown towards the white dwarf. So this sort of slide I'm showing here is for a young and hot white dwarf. So we are at 30,000 Kelvin and a cooling age of 0.02 gigayear. So this is very new into the white dwarf's lifetime. Again, we have a size proxy on the y-axis and a distance on the x-axis. The asteroids start from the right-hand side and move into the left. So there's quite a lot going on in these graphs. So I just want to say that because we've already sort of discussed shape, I'm not really going to focus on the colors in these individual lines, but more so on the markers. So these circle objects here, these circle markers here, indicate that large bodies are fragmenting. So basically any body that's larger than 100 meters, regardless of the material it's made of, will fragment. And you can actually see the diagonal lines that were sort of present in the previous plot in these results for our simulated main belt asteroids here. And when you go down to much lower sizes, so sort of tens of centimeters and smaller, you get a lot of material sublimating. So all of these smaller bodies, which are going to have, which are going to be part of these larger bodies, which are maybe disrupted, are going to be sublimating completely due to the intense stellar radiation from the star. And you get this material out to quite large distances. And for this particular white dwarf example, you also get a small range of sizes of material which impact directly onto the surface of the white dwarf. Now, if we move to a slightly older and colder white dwarf, so this time we're talking about a 4,000 Kelvin white dwarf, so and a cooling age of 9.8 gigayears, the situation changes quite a lot. Especially for the smaller material. So in this one, for objects which are larger than 100 meters, still you're seeing the fragmentation from before. That doesn't change too drastically. But for the much smaller objects, we are seeing a large reduction in the sublimation, perhaps not unexpectedly due to the reduced amount of radiation from the central star. But you're seeing that there's quite a large amount of material which is able to impact directly onto the white dwarf, which is an interesting consequence of this sort of model that this analytical model that we present in this work here. So this sort of maybe suggests that as a white dwarf cools through its lifetime, we should be able to see that there is a difference in the amount of material, or the material that we would expect to see around a white dwarf. So your young and hot white dwarfs should have sort of more gaseous material, whereas as you get older and colder, the production rate of this gaseous material will, will reduce. So just a sort of a little summary here. So just to go back over some of the results. So for fragmentation, so tidal disruption events, this dominates for all objects which are larger than 100 meters due to the fact that they are less materially strong. And fragmentation can be well approximated by a spherical model. It's not necessary to look at ellipsoidal shape models when using an analytical model. Whereas for sublimation, there is quite a large difference in there's quite a large effect that the shape model has. So the more elongated your asteroid is, sorry, the more elongated your asteroid is, the more likely it is to sublimate further away from the white dwarf. And as the white dwarf cools down, you get less sublimation, so you end up with more material being able to directly reach the white dwarf surface without undergoing further disruption through tidal effects. And one sort of like outcome which I want to highlight particularly for this model is that we can use this to quickly determine the probable outcome for any planetesimal of any arbitrary size, material, or shape. If that were to approach a white dwarf, what would happen to it? We can quickly determine that. And sort of applying this model to specific observed systems is coming up in some future work, hopefully. So please feel free to see this paper, which came out last year in MinRes. The reference is down here if you want any more details. And I'm happy to answer any questions.
Excellent. Thank you very much, Kat. That was really, really nice. Very good presentation. Do we have any questions? You can either raise your hand or put it in the chat. Okay, while people are coming up with their questions, I have one of my own. So you showed two models for white dwarfs, one with the temperature of 30,000 and the other one I think was 40,000. Is the idea behind that like you can have things from the asteroid belt falling onto the white dwarf at any point during its cooling down, or is it because you're also thinking of exo asteroids like, or exo comets like O-MESS2 VIII?
Yeah, so it was sort of to try to understand how the debris that we observed might change as a white dwarf cools down. So if we look at a particular white dwarf, what would we necessarily expect based on its temperature at this particular time? And then it sort of so yeah, there is a slight thing here that we are assuming that there is the same amount of material available for all of these white dwarfs at all parts in their life. Yeah, so actually in the full paper, we considered a range of temperatures across from more than these two, just to see how it effectively changes based on that. Yeah.
Thanks. Andrew Swan has his hand up. You can go ahead.
Hi, Catriona. What kind of inputs do you expect to your model? Because you mentioned the effect of radiation early in the white dwarf phase.
Yeah.
And I know we should expect things to break up a bit, but yeah, what goes into your model?
Yeah, so it's actually, the sublimation specifically is quite simplified in this model. So we sort of consider just the pure power that's available from an incident radiation and how that causes mass loss directly. So I think one aspect of this work that I sort of probably should have outlined more is that I really want more sophisticated sublimation models to maybe look at how this shape model further affects it, because this is just from the simplified, like how does the incident power from the star itself affect it as you get closer in, as the radiation increases. Sorry, I hope that answered your question.
I think so. Does it take account of, well, I think you just said it doesn't, but what happens if you take account of like radiative spin up?
Yes, okay, yeah. So again, yeah, we don't consider how the rotation of these asteroids change as during this sort of analysis. Yeah, you're right, as because we are looking at these sort of elongated shapes, there will be sort of a more intense radiative spin-up effect because there's a greater surface area to the shape to sort of induce the Yorp effect. So I would probably assume that we would expect like more elongated shapes would probably spin up before they sublimate completely. So you would have that as an additional sort of disruption route for this model, definitely.
Okay, cool, thank you.
Okay, we have a question in the chat from Uri Malamud. Could you outline perhaps how this relates to fragments which do not move directly towards the white dwarf?
Yes, yeah. So in terms of this model, assuming that the object has a pericenter inside the white dwarf, and so we can consider that it's effectively moving on a straight line, it doesn't necessarily change too much if you change that assumption, because the moment when the asteroid is approaching the white dwarf from any sort of orbit, you can essentially, well, assuming it's an eccentric orbit, you can assume that that body is effectively on a linear orbit. So the only part of this that would massively change is that the body would not impact directly onto the white dwarf if its pericenter was a little bit larger. But the effect of the rest of the model doesn't change drastically if you're looking at slightly less eccentric orbits. It wouldn't be applicable to sort of more circular orbits, but for large eccentricities, so sort of 0.9 and above, it wouldn't change too drastically.
Excellent. Uri says thanks. So I don't see any more questions at the moment. So thank you again, Catriona. And we'll move to our next speaker.